Alright, let's get it on. I'm gonna be solving this hard problem, create sorted array through instructions, 1649. Given an array instructions, you're asked to create a sorted array from the elements in instructions. You start with an empty container, nums, and for each element from left to right in instructions, insert it into nums. The cost of each insertion is the minimum of the following. So 1 is the number of elements currently in nums that are strictly less than instructions of I. Hello, smart coder. Thanks for joining. And so it's the minimum of either the strictly less or the strictly greater at that point of the execution of the instructions. And we have an example, and we have to return the total cost to insert all elements from instructions into nums. And since the answer may be large, return in modulo the usual billion plus 7. So let's write this so that we don't forget. Write this down. Alright. We have 3 examples with details of every insertion, which is nice. And here the constraints are, they're up to 10 to the 5 instructions, and the values of the numbers to insert are within 1 and 10 to the 5. And this is interesting. It's going to be useful. So let's start solving it in a brute way and see where it leads us. So one way to solve this would be to just put in instructions. So this problem boils down to keeping track of the elements that we have inserted so far, and for each element in instructions we want to count how many there are already there that are strictly less and how many are strictly greater. Then we just get the minimum and we add that to the result. So it boils down to having those two operations, the number of elements that are strictly less, the number of elements that are strictly greater. One way to do this that is simple, but it's probably too slow, it's to just have an array, a counter array, which is going to have a position for every possible value that we have, and in that position we're gonna count how many occurrences of that value we have so far. So let's do that. Let's have a count that has the size of the maximum instructions plus 1, so that we have an index for the maximum as well, from 0 to the maximum inclusive. Initially we don't have any occurrences, it's empty, and then, like we said, we add the minimum between the numbers that are strictly less, which are going to be the sum from the beginning of count up until e, without including e, because it's strictly less, and for the strictly greater, we want the sum from e plus 1 till the end. We should not forget about modding, and here we add, once we computed that, I mean, we can do it before and after because we're not counting this value, but it doesn't matter. And we count another occurrence of value e, and here we return result that I did not initialize. It's initially 0. Alright, so yeah, let's call this x. Why not? So it solves the problem technically, but it's probably too slow because for each operation, and there could be 10 to the 5, we are going over the entire array actually. So it is quadratic. So for big cases, I mean, it solves the examples, but for big cases it's going to take 10 to the 10 operations, and that's obviously too slow. But let's speed it and get the TLE, so that motivates us to optimize this. Let's see. Maybe the test set is weak. Well, it was pretty close. I mean, it solved 56 examples, test cases, so not too bad. I was expecting this to be worse, to do worse than that. Okay, so now that we pushed this solution this far, now we introduce the segment tree, which is the title of this stream. And why did I do it this way? Well, the idea is that the segment tree has a very similar interface like this array. I mean, the interface is an array which also has indexes from 0 up to some maximum value. But the difference is that we want to do these sums quickly. We are also going to be adding the occurrences to the value index, but here the thing that is slow is this sums. So we want this kind of array on steroids that will provide the sum for, in this case we're only doing prefixes and suffixes, but the segment tree will give us the possibility of adding any range query, in this case of a sum. Okay, so the idea is to represent the array as a complete binary tree the same way that we represent a binary tree, a complete binary tree with heap sort, for example. We represent it as an array, and since, okay, let me write down the tree for one of the examples. Let's look at example 3. Here we can translate it first into the this representation. Let's just print out count, but after, wait, because at that point it's going to be let's run it. Okay, so it's 0. Well, there are no zeros because these numbers are 1 from 1. There are no zeros, that's why this is 0. Then there are two ones, 3 2s, and 3 3s, and 1 4. And the size of the array is 5. So, like we said, there's a 0 here. 2 3 3 1. 2 3 3 1. So this is what I like to call our logical array in the context of the segment tree, because we're going to have essentially 2 arrays. The logical array, which is what the user knows from the interface, and then we're going to have a physical array, so to speak, that it's going to represent the binary tree, the complete binary tree that will include internal nodes in order to compute this range queries quickly. So here the indices are 0 1 2 3 and 4. The size is 5. Okay, so what is going to be the corresponding binary tree? So the size of the tree, it's going to be we're going to store these values in the leaves of the tree. So we are going to have 5 leaves and 4 internal nodes. This is always, this relationship between leaves and internal nodes is always true for full binary trees. It's a very well-known theorem. This is going to be a complete binary tree and also a full, well, both of them. It's not, they're not the same. Complete means that all the levels of the tree are full except for the last one, and in the last one all the nodes are to the left, whereas full binary tree means that every node has either 0 or 2 children and not only one. Okay, so like we said, we have 5. So we have 4 internal nodes. That means that we're gonna have the root, the left child, right child, and then these are the first, let's call this, let's enumerate them. This is going to be node number 1, 2, 3, and 4. And these are the 4 internal nodes. And now we need node 5 is going to be a leaf, node 6, 7, 8, and 9, and there we have all the leaves. I'm gonna color them so that it's clear they are special. That's where we are going to store our values, the values in the logical array. Okay, and so let's number them. Let's keep numbering them. Again, these are the indices of the physical array: 5, 6, 7, 8, and 9. I'm just going from left to right on each level. And so this is the first leaf, and this is going to represent 0. This will have a 2. I'm just copying whatever is here. A 2, a 3, a 3, and a 1. Okay, so now I have the leaves, and like I said, this is going to be 0 in the logical array. 1, 2, 3, yeah, and 4, which are all the numbers here. All right, so and now we want to put something in the inner nodes, in the internal nodes, so that we can answer the range sum queries quickly. So what we're going to do is we're going to add the sum of the children. So in this case it is 4, and in this case it is 4, and 5, and 9. All right. So notice that when to get to the children of a node, for example this node which has index 3, the children are 2 times 3, so 6 is the left children, the left child, and 2 times 3 plus 1 is the right child, 7. This is the same way that, like I said, like you do to represent. So in general, if this is k, this is going to be 2k, and this is going to be 2k plus 1. And that also means that if you want to go to the parent, if this is k, and you want to go move up the tree to its parent, it doesn't matter if it's a right child or a left child, k divided by 2 as integer division gets you the parent. And this is very useful to move up or down the tree. And so I think here we have all that we want. Notice that we started numbering from 1. This is for convenience, for these formulas to work. That means that we're going to leave the 0 index of the array unused, but it doesn't matter. So then we're going to implement 2 operations on this tree. One is the add function, which is going to receive an x and a delta, or Well, I mean, we can assume that this delta is 1, which means that it's going to add one occurrence of x. So let's say that here, let's work it out in this example. Let's say that we add one more occurrence of 1. We add, so x, let's say x is 1. That means in this array, we just update the 2 with a 3, okay? But here, we first need to find the position that corresponds to 1, right? And the way to do that is to add n. So, like I said, here we get the index in the logical array, but we want the index in the physical array, the array that represents the tree. And you get there by adding n. So we start with a 1, we add 5, we get to 6. So now we're on the leaf that corresponds to value 1. We have a 2, we increment it, so we get 3 now. But now we have to update all the parents, all the ancestors of 2, which are the ones that are affected here. So we go to the parent, which we do like we said here, by dividing by 2, and we add the 2, which is going to be incrementing this by 1. So here we're going to have a 6 now, and here again we go up and we're going to have a 10. So that's how we implement add. We go up until the root, updating all the ancestors of the node that we changed. So that's easy enough. Then we want to implement another function, let's call it sum, that it's going to implement the range query, the range sum, and it's going to get now 2 positions, left and right, and let's make them inclusive just for convention. And so for example here, if we ask for, I mean, it's going to do the same that we did here with the sum and the slices of the arrays. So here if we call from left equal 1 and right equal 3, we have 3, 3, and 3, so it has to return. So like we said, if it's 1 and 3, it will return 9, and so on. But now let's start implementing what we already discussed. Will the sec tree always have 2n nodes? Yes. Well, not exactly. Like I said, the position, it's going to have an array of size 2n, but we leave position 0 unused. So it's exactly 2n minus 1 nodes. But yeah, that's a good question. It's unintuitive. Yeah, that is, let me clarify, but that's the idea. Since we're going to have n minus 1 internal nodes, so you can think it in terms of an example. For example, if we are asking for position 0 in the logical array or in the interface, however you want to call it, then you know that you're going to have n positions at the beginning of the array which are going to be non-lists. So that's why you need to skip n positions. So 0 is going to correspond to n. Are you following? Do you want me to? Maybe it's going to be clearer here. So let's write a class, segment 3. It's gonna, okay, so it's always gonna be split between first half is the tree, second half is the actual values. Yeah, that's a way. I'd like to say that the second half is also the tree, but only but they are the leaves. But yeah, I think it makes sense what you're saying. So this is the constructor is going to receive n, which, like we said, it's going to be the size of the logical array, and we need to save that because we're going to use this to translate ID indices, like we just said, and then we're going to need the actual array to store the values of the tree, which initially is going to have all zeros because there's nothing, it's empty at the beginning. And like we said, we want it to be of size 2n, n times 2, and that's all the initialization that we need. Then let's implement the add method that we already explained, that we discussed. Is going to receive x and a delta, which is going to be 1 by default. And let's do this slowly. First, we want to translate x. It's an index in the logical array. We want the corresponding index in the tree field. Okay. So for that, we add n. We need to skip the first n positions, which are the unused value and the internal nodes. Okay, we skip that. Now we are at the leaf that corresponds to the original x. Okay. So what we do, we just use that index and we add the delta to it. Okay, so now we have updated the leaf, but like we said in the explanation, we have to move up until we get to the root. So one way to do this is to, well, like we said, we divide by 2, integer division. Now we are at the parent of the leaf, and we want to do that while x is greater than or equal to 1. 1 is the root. We want to include it, and here we want to update the value of each of these nodes by adding up the values of their children, which are 2 times x plus 2 times x plus 1. And we divide by 2 again, and that is all. That's it. And then we want to have the I'm doing the iterative implementation, which is it's more efficient in practice, especially in Python. yes, also the sum is going to be iterative. Yes, the recurse, I'm used to this implementation, which is a little quicker. There are some advantages to the recursive implementation, but they are more advanced. Is to implement lazy propagation, I think. But we're not going to get into that. Yeah, self. Good point. Okay, so I want to give them, since we are in this problem, we are going to be using only prefixes and suffixes. I'm going to, oh yeah, I always forget about this. I let the IDE to complete that for me. So what I'm saying is that I want to give left and right default values, so that they're not mandatory. And so if right is none, we want right to be n-1. Okay, this is just for convenience, so that you don't have to set both if you, or neither. Okay, so now again, we want to translate the indices. How do we do that? We just add n, so we get to the leaves. We skip the internal nodes, we get to the leaves. Now we're gonna keep, now we have to return a value which is going to be initially 0, and no, I think that doesn't work, because you cannot refer to self in the parameters. That's why I'm doing it this way. But I tried it and it didn't work. So left and right represent a range, an inclusive range. So as long as one left is less than or equal to right, we still have a range. So essentially what we're going to do here is, like, first we have a range in terms of the leaves in the lowest level, but we're going to be moving up until we converge into one node, which is going to have the aggregation, the sum of all the range, the entire range. And well, one thing that I did not mention is that since all of these functions are moving up the tree, this both are logarithmic, because this is a complete binary tree. The height must be the logarithm of n. So, well, let me explain what we need to do here. Eventually we are going to go to the parents, okay, but of left and, but here there's some important stuff that I'll explain here. So let's consider the left pointer, the left node. So we want to move up. I mean, this is the left node, and somewhere in here we have the right. No, this is left. Okay, and essentially we want to move up, but there's a catch, because if left is a left child, that might be confusing, but left here means left of the range, and left in terms of the child, it means that it's the left child of its parent. Okay, those two different uses of left. So if it is a left child, then we can move up, and this node will include the value here, whatever value this has, because of how we constructed the tree, and we're gonna be within the same range. Okay, and in that case we don't have to do anything, that's fine. But what happens if left is a right child? Then there is a problem, because in that case the parent is also going to include this left node, and this could have some wacky value, whatever value that we don't want to. It's not part of this range that we're interested in. So what do? We cannot just go up. What we do is we jump to the next node, which is going to be a left child, not a right child as this one, so it's not going to have that problem. But when we jump, we need to add the x value into the result. Okay? That's important. And how do we know if it's a right child or a left child? We said that if it's, the problem is when it's a right child, and we know that when it is a right child, it's gonna be odd, because it's 2 times this index plus 1. That means it's odd. Okay, so do you follow? That translates very directly into code. We said if it's a right child, which means that left it's odd, then we want to include the value of left in the result, and we want to jump to the next node. Okay? And the same for right, but in the opposite direction. The problem with right, if it's a left node, which means that it's even. If it's even, then we need to add this, and we jump to the node to its left. And that is it. It's pretty simple, really, when you think about it. And it should do it. So now we have to translate the code a little bit, but it's the same idea. Here we want a segment tree, and this is going to be n. That's correct. I mean, the size has to be the same as the size of the array that we used before. Then instead of doing this, we want to use the add method of x, and the default is 1, so we are fine. And now we need to translate this. So we want sum of, in this case we want the right to be x minus 1, and in this case we want left to be x plus 1. And this is it. This is pretty much it. Notice that if x is, well, x cannot be 0, because in this problem x is at least 1. But if it were 0, even if it were 0, we would have right equal -1, but then left would be 0, and this condition will fail, so the result will be 0, which it makes sense. And the same goes here if this is the maximum value and left exceeds the maximum value, and right will have the maximum index, but then we won't enter here, and then the result is going to be 0. So this works for the edges as well. So let's see. Yeah, I'll repeat it in a moment. Let me see what's the problem here. Oh, I forgot to. Yeah. Okay, it passes the example, but we erase the examples. Hey, thanks, Raimundo. Thank you for the follow. How do I restore the reset here? Okay. Let's check it out. All right. And we passed. Cool. GG, indeed. So you wanted me to repeat, why don't we just directly. So the sum method. So, well, first of all, if this is where we actually add something to res, right? If we didn't do this, res would be always 0. But yeah, let me repeat what I said here. Okay, so what I was saying is that, let's say that we have our left pointer points to this node which has value x, and then we have the right pointer to this other node, okay? And we want to move up until they converge, and we find the node that represents the whole this whole range, okay? But what I said is that we need to be careful, because if this left node is a left child, then that's fine, because this node, the parent, let's call it P, it's going to include X and nothing else, and it's going to be within the range that we care about. So in that case it is fine. But what happens if it's a right child? The problem is if it's a right child. If we just move into its parent, into P, without doing anything else, then, for example, we would include the left, also the left sum, because every node, it's a sum of both children. So if we just move to P, we're going to include this node that maybe has some other value, some infinite value, whatever, but it's not in our range, so we cannot move to P. Are you following? So we have to do something else, and that something else is to jump into the next node in the level, which would it be better? Oh, here. No. Are you following this? I prefer to make things abstract and not so concrete. Are you confused by something in this diagram? Because this translates to the code that I'm writing, and this is just an example. Jump. Yes, jump, I mean, remember that we numbered all nodes by level. So we number this node 1, this node 2, this 3, 4, 5, 6, 7, 8, 9. So by jumping, I mean moving to the next node in the same level. Okay? That's what I'm trying to get to here. So if this is index left, this node has index left, so this is going to be left plus 1. Okay, if you can read that. So the strategy that I'm proposing is to jump. Yeah, maybe this arrow that I'm drawing is not clear because it's not really an arrow of the tree. Sorry about that. But yes, I'm just maybe some dots, some dotted line, whatever. So we're moving to the next node in the level, the same level. And we are guaranteed that this is going to be a left child. And we like left childs in the left side of the range because of what we said before. But what happens if we skip x? We cannot forget about x. X was part of our range, so we have to add x to the result. Okay, so that is it. And the same thing, the same logic applies to right, but in the opposite way. So the problem with right is when it is a left child, and in that case we want to jump to the one to the left, which is right minus 1, and that's it. And then we ask, how do we know if left is a right child? Well, it's when it's odd. And how do we know if right is a left child? Well, it is even. And that's exactly what we wrote here. If left is odd, then we add the value of left and we jump to the node right to its right. Yeah, it's pretty clever. I did not invent this. I'm not taking credit for it, but yeah, it's pretty clever. But it's good once you understand it. It's pretty simple, I think. I can code this by heart because I remember the concepts. So yes, I think this maps to this explanation pretty directly. I'm gonna share the code here so that you can check it out, and you can even reuse it. I mean, it's reusable. This is not really mine. You can reuse it in your solutions as well. It's good to have it in a library. But yeah, no problem. I'm here to help. So what else? I wanted to mention a few follow-ups or generalizations. So here we are using the tree to implement something like a counter, because we're counting the occurrences. Well, we're also implementing deletions, right? Because this delta could be -1, and in that case we're deleting numbers, so the add can also be a remove, and you can pass any number you want. That's gonna work. But also segment trees work with any. Here we're assuming the function to be addition, but you can use any other function. You can use the minimum, maximum in a range. You can use a GCD, greatest common divisor. You can use whatever. I mean, it doesn't even have to have an inverse. For which n is this going to start TLEing? Well, this is n log n, so it should never TLE, because the size of the is pretty close to linear. So as long as they are passing you the size of the array, the automod just held a message. Yeah, I think that 10 to the 9 is some kind of obscene drawing or something. I don't know. It's some kind of phallic thing. Anyways, no, what I'm saying is that even if it was 2 to the yeah, I see what you mean. Yeah, that's another point that I was going to explain about index compression. Yes, here it is convenient that the numbers have values within 10 to the 5, right? If the values were bigger, they could be even 10 to the 18 or something, and we would have a problem because we are creating an array of that size. So yeah, that's a good point, thank you. But that's when index compression comes in to save the day, because even if the values are in whatever range, they're negative, they're minus 10 to the 18 up to 10 to the 18, the number of unique values that you're given is still bounded by 10 to the 5. So what you do in that case is you create what it's called index compression. It sounds fancy, but it's just to create a mapping. The values that you are going to be, you just add the values into a set to remove duplicates. You sort them because you only care about the order, you don't care about the quantities. And then you enumerate them to assign them an index for ix, and then you create a dictionary from the value to the index so that you can translate them. And and then instead of using this as the maximum value, you only want the number of indices. So for example, if there was only one value, like 0 for example, yes, I think you don't even need the +1, and then every time you use this, yes, I guess you can just translate this into an index by doing doing this, and then you replace x by I. And that is it. And in this case, it doesn't matter what the ranges are. See? So yeah, this is very, very important trick to make this work, because in many cases it doesn't. Yeah, it's pretty cool. I mean, the code is very simple. You should remember this line, because you only that's mostly what it takes to apply this trick. Let me share this version as well, so that you can remember it. But I'm glad you like it. What else? So I mentioned that you can use any other aggregation function. You don't even need an inverse of the. So if you a simpler way to solve range queries is to use prefix arrays. The problem with prefix arrays is that you cannot resolve dynamic queries, only static queries. That's why segment tree, you need a segment tree for this problem. But also for prefix arrays, you need to have an inverse, because when you want an arbitrary range, not a prefix, you need to cancel out the prefix that is duplicated. And for example, if it's a minimum, if you want the minimum of a range, you cannot use of an arbitrary array, not a prefix, then you cannot use a prefix array, but you can use a segment tree. Because here we're not canceling anything. We're just computing the range. We're breaking down we're breaking down the range into pieces that are powers of 2 and that are in total logarithmic in size. So it's very versatile, this data structure. So and also one other advantage is that it does everything that a Fenwick tree, which is a very similar data structure in terms of the operations that it can do. But the segment tree can do everything that the Fenwick tree can and more. So that's why I don't recommend to learn the Fenwick tree, and I think it's harder to understand. So I think you're covered. The segment tree dominates the Fenwick tree, and you're covered knowing this. Then, like I said, there's no binary index tree or bit is the same as the Fenwick tree. It's an alternative name. Segment tree is I don't think it has an alternative name. And And in some contexts, I think segment tree means different things. This kind of segment tree, I think it's like part of the folklore of competitive programming. So be careful if you search it on Google, you may end up in articles of different data structures. I think I first learned this implementation from the competitive programming handbook, I think it's called. But I incorporated some tricks, which is what I explained here. So, I mean, you can go to that book and check it out. Oh, you're saying this is bothering you? Yeah, I didn't think about that. We can check out more optimizations for this code. I mean, we could do like micro optimizations, like instead of dividing by 2, doing like a shift. I don't think it's worth it, but yeah, probably this is not gonna make any difference. But well, this is going. So I know an alternative solution, which is to use a sorted list. But more optimizations. No, I think this is pretty tight. Maybe there are faster solutions with different. Well, let me check the from sorted containers, import sorted list. TLEs. Which one? TLEs. And here, how do we do this? We want cell bisect left x. Yes, that's going to give us all of the numbers that are less, and cell bisect right of x. This is going to give us all the numbers that are strictly larger. I don't follow. Let me try this before opening that link, or if you can explain it. Okay, this is faster. So maybe that's why it's 25%. But don't worry about that. I mean, think about the order of complexity. I think the implementation is pretty tight in terms of the constant if you do it iteratively. And I've solved many problems with the data structure. Yeah, of course, there are many cases in which you can use the sorted containers, the sorted list, which is maybe easier to use, and it has it's more flexible. You don't have to do index compression, stuff like that. TLE where in oh why are you using a class? I don't know. I can help you debug it offline, but this was faster. Let me share that as well to make it in the stream complete for the sake of completeness. And yeah, this is a Fenwick tree. Yeah, the Fenwick tree, I mean, even though the segment tree dominates it in terms of order of complexity and the things it can do, I think it's, in terms of constant, it might be better. But I wouldn't worry about it. I mean, if you're interested, of course, by all means, study it and use it. But if you want to optimize your time, I would suggest to give priority to the segment tree. There are many things to learn. So yes, that's all I have. Do you have any other questions? This is something that I found which has this theorem that I mentioned, that the number of internal nodes is always one less than the number of leaves in a full binary tree. I'm going to share this as well. I'm not sure if anyone is interested, but for the sake of completeness, no problem. Yes, practice them. There are many. Whenever you see a problem that can be, yes, one more thing that I wanted to say was that you can also solve the kth smallest element problem with the segment tree. Which is the order statistic problem, which you can also solve with the sorted list, but in that case you need to do a binary search with the segment tree. because if you know, so you remember what the kth smallest element is. So you can do a binary search. You're searching for the value such that when you sum from the beginning up to that value, you get a total of, the sum is a total of k elements. So when you move to the right of the value that you're finding, the sum will be greater than k, and if you move too much to the left, the sum will be less. So that gives you the information to eliminate halves of the search space, and that's how you do a binary search. So that's another thing to take into account. It's can be very useful. So yes, you can use it in many kinds of problems. So, well, I hope you liked the session. I'm gonna end it now, and I'm trying to maintain a streak of streaming every day, maybe. Well, today I did it twice, so maybe an average of every day. I have a so we'll see how it goes. Well, thanks guys. I hope you liked it. Bye bye.